Hello and welcome. This is chapter number 10, Sinusoidal Steady State Analysis of our Sadiku's textbook. In this lecture, we'll be solving how to use Thevenin theorem and Norton theorem to solve AC circuits for steady state analysis. So let's start by solving example 10.8 of our textbook. So in this example, it is said that we have to obtain the Thevenin equivalent of the circuit that is shown over here. So remember, the Thevenin equivalent for any circuit will always be taken against any two terminals. Or for example, if we have a circuit something like, say we have a circuit like this. So this is our C, this is L, this is R, and this is our input source, and say this is our output resistance. So if for example, if we have a circuit like this, so and if we have to find out the Thevenin equivalent for the circuit across these two terminals, so the Thevenin equivalent of a circuit will always be across any two terminals. And generally when we solve this, we have to basically make an equivalent circuit that looks something like that. So this is Z Thevenin and something that is RL and this. And remember, this concept is extensively used when we do or when we use the concepts of maximum power transfer out of any circuit. So now in this example, so let me first remove this. So a Thevenin, so before that, so Thevenin equivalent will be an equivalent circuit that sums up whatever the input voltage over here is applied, what is the actual or the Thevenin equivalent voltage that is appearing across these two terminals, along with the resistance that is seen by an observer if that observer is standing over here. So whatever the Z Thevenin or the Z input that is seen by the observer over here, and the effective voltage that appears across the terminals. So once we have this, basically this the equivalent Thevenin model would be for this circuit would look something like this. So let's use this concept of Thevenin equivalent and solve this circuit for AC analysis, for steady state AC analysis. So here what we see is that all the components or all the passive components in this circuit along with the voltage source are given in their phasor form. So they are not in their time domain form. So if they were in their time domain form, we could have just simply convert them into their phasor form and do the analysis. So the circuit is already in its phasor form. So let's first of all, or the first step, we have to calculate the Z Thevenin or Thevenin equivalent impedance. At terminals AB. First of all, let's calculate this. So the first case when we have to calculate the Thevenin impedance, remember voltage source. If there is a voltage source in a circuit, that voltage source is short circuited. And if there is a current source, that current source is open circuited. So here we have a voltage source. We just simply short circuit this and measure whatever the resistance we get at these two terminals A and B. So let's see how or what we get. So we have we have a bridge network. We have a capacitor over here. We have a resistor over here. And this is terminal A. This is terminal B. This is terminal, and this is 8. And this is, sorry, J12. This is 8 ohms. This is minus J6. This is 4. And this thing is shorted. So just simply short both of them together. So now it's always good to label it A, F, this is E, sorry, this is D, E, F, this is C. So now basically we have to find out what is the effective impedance that is seen at this point. So we simplify the circuit. So point D and F are at same potential because they are shorted together. So we can basically uh, draw this circuit in a manner in which we can say that F and D are at same potential. Uh, so it can be drawn in a way like this. This is 8 ohm. Uh, uh, you can take this side of 8 ohm and move it over here. So this 8 ohm becomes in parallel with J6. Uh, and this J is connected with F over here, F over here. And similarly, this J is connected, sorry, with the D, this D, so D, so F, I have brought this F over here. And again, this F is also connected with uh, J12, and this J12 is also connected with C. So technically, this is how it goes. A, this is B, this is C, this is 4 ohms, and this goes to D over here. This is A, this point is E, and this is F. E is also connected with F. So this is how the circuit looks like. So all we have to do is find ZAB, and that will be equal to my Z-Thevenin. So that Z-Thevenin is basically uh, these two parallel combination of 8 in parallel with minus J6 and parallel combination of 4 in parallel with J12. So the effective impedance would look something like this. This is A, this is B, and this is 4 together. So this is 8 in parallel with I call it as Z1, and I call it as Z2. So this becomes my Z1. So my Z1 is minus 2.88 minus J 3.84 ohms, and my this is Z1, uh, and this is Z2 as 3.6 plus J 1.2 ohms. Right? So this is how parallel goes. So if I'm going to measure A or B over here, to ZAB or Z-Thevenin will be equal to Z1 plus Z2. So my Z-Thevenin will be equal to 0.72 minus J 2.64 ohms. So this is the effective Z impedance for this circuit. So now my second step will be to calculate. Now what we have to do is to calculate V-Thevenin. So our circuit is something like this. If we are going to draw it in a much simpler way. So this is the capacitor, and this is an 8 ohm resistor. This is again a resistor, and this is a inductor, and that is connected to a 12 angle 75 degrees. So this is how our circle also. So for example, this is point D, this is point F, this is minus J6, this is 4 ohms, this is 8 ohms, and this is J12. So this is again A, and this is B. So the easiest thing is to find out what is the current that is going in this branch, and find out what is the current that is going in this branch. Find out both I1 and I2 first. So for I1, remember I1, again, this is equal to the total voltage, because this voltage source is in parallel against these both branches. So the voltage will remain same, divided by the total impedance of this branch. So it is 8 minus J6. This is my I1. Similarly, my I2 will be equal to Again 12 angle of 75 degrees divided by 4 plus j 12 amperes. So this is both my values of I1 and I2. So remember, then VThevenin voltage, VThevenin will be voltage at A minus voltage at B. So voltage at A, how we are going to calculate this voltage? So this voltage will be the voltage drop across this, and the voltage drop across 6j element, and the voltage drop across this 4 ohm resistance. So so if we have to so actually what our circuit would look like if I draw in a more simpler manner. This is the voltage we have to, so this is V Thevenin plus and minus. So if I have to write a loop equation, it would be something like this. So this equation would be V Thevenin equals to minus J6. So the current, if flowing in this direction, so I, it will be minus of I1 that current goes through plus 4 and angle of the current of I2. So this will be the overall the equation for what is the value of, or how we are going to calculate the value of VThevenin for this branch. So just now how to calculate VThevenin minus J6 into minus I1 plus 4 into I2. So remember, Thevenin voltage is minus J6. I1 was 12 angle of 75 degrees divided by, it comes with the minus sign here, minus J plus 8. This one was I1 plus 4 into I2 was 12 angle of 75 divided by 4 plus J 12. So this one was this. So my overall voltage Thevenin, V Thevenin will be 37.947 angle of minus 139.695 degree volts. So this is how we calculate VThevenin. So overall, the Thevenin equivalent. So if we have to find out or equalize, or we have to develop a Thevenin equivalent circuit. So the Thevenin equivalent will look something like this. So VThevenin over here, and this is our Z Thevenin over here, and this is A and B. This is Z Thevenin, where VThevenin value is 37.947 angle of minus 139.695, and Z Thevenin value is 0.72 minus J into 2.64 ohms. So remember, if a question like this has been asked, or in an exam or in any situation you are asked to develop a Thevenin equivalent of a circuit at any of the two terminals, your final answer will have to look something like this, because that basically shows that you actually know what or how a Thevenin equivalent circuit looks like. And again, you have to basically calculate the V Thevenin value and Z Thevenin value as well. So this is how a Thevenin equivalent for our circuit like this would look like. So let's move ahead and see and solve our next example. So in example 10.9, again we have to solve a Thevenin equivalent for a circuit that is shown in this figure, and this is the figure 10.25 from the book. Again we see that we have two terminals, terminal A, terminal B, and at this terminal we have to find out the basically what. So if we are standing here, if a person is standing here, so we have to find out Z Thevenin and V Thevenin at this location. So again, this circuit has been already converted into phasor form, so we do not need to convert the circuit further into a phasor form. So first of all, what we have to do is we define nodes. Uh, so let me call this node A, or maybe this B. So I have at node A. So at node A, what we are seeing is that we have a current source that is giving a current input. We have current of I naught going over here, and we have this dependent current source, and this value is zero point 0.5 I naught. And this zero point 0.5 I naught is going here because there is no branch, or this is an open circuit. So 0.5 I naught is given here. So we can calculate I naught from there as well. So we have 15 angle of 0, that is current entering the loop, and the other two are leaving. So leaving the loop are I naught plus zero point 0.5 I naught. So easily we can calculate 1.5. So we can just simply uh, say that I naught is equal to 10 angle of 0 amperes. So this is the value of I naught we have. Now, this is if we see uh, that this is the loop that is, or this is the uh, main loop which we are concerned. So if we applying KVL on this, you can say on path A, B, C, D, we're applying this on this path. So what we see here, so if we see that at 4 into this is again 0.5 into I naught, because this is 0.5 I naught current that is flowing, plus J3 into 0.5 I naught. This is the current that is flowing, plus whatever the voltage. So this is we have to find out V-Thevenin over here. So this is the equivalent to V-Thevenin plus V-Thevenin, then plus again. So this is minus 4J plus 2J. This is the 2J plus minus 4J. This is the current, and in this loop we have I naught current flowing, and we are applying KVL, so they are going upward direction. If we are going to make this loop, so it would be minus I naught, and this is equal to 0. So this is the complete voltage, or we can also call it VAB equals to V-Thevenin. So this is how this whole loop will look like. So if we are going to just simply calculate V-Thevenin from this loop, this V-Thevenin value will be equal to minus J55 volts. And remember, minus J55 is 55 angle of minus 90 degree. Again, this is in terms of volts. So then, so what we have done, we have calculated the V-Thevenin for the circuit. Now we have to calculate, now calculate Z-Thevenin. Z-Thevenin. So calculating Z-Thevenin, remember, uh, calculate Z-Thevenin. So what we have to do, we have to basically short the voltage source, they become short circuit, current source, open circuit, right? But if we so we apply this concept over here, so what we are left with, we are left with something like this. So this is something what we are left with, and we are standing here, and we have to find out Z-Thevenin at these 2 points A, B. This is 4, this is 3J, this is 2, this is minus 4J. So this is how we know. So such a circuit, in such a circuits, we always introduce a dummy current, a dummy source. So it can be a current source, or it can be a voltage source. So here we introduced a dummy current source because we are having a independent current source. So we call it as IS. So this current dummy current source is, say, connected over here, and this current source provides current is from over here, and the voltage provided by this source will be vs. So we can let is equals to so your textbook basically uses 3 angle 0, so you can use any value, there is no particular reason why they've used, just it will make the calculations more in whole numbers or better controlling decimals rather than any other. There is no point. You can always use as 1 angle 0 or any other value. So if we have this current source over here, what we get, so at, say this is point B, so at B, so at B we have current entering the loop is equals to current leaving, so current leaving 1 is this is 0.5 I naught, and this is already I naught, so the plus current is I naught. So uh, 1.5 times I naught equals to is. So if is will be 1, your value will be I naught will be um, um, so so that is why they use 3, so that will give you I naught value equals to 2. So so instead of using the book's value, let us use value of is is equal to 1.5 angle 0 ampere. So this will make it a little different from the textbook, so that you can see that any value can be changed. So if this is the value that is taken, so I naught value is uh, equal to 1 angle of 0 amperes. So this is the value of I naught if we use this value. Now I have the value of I naught. So now I just apply the uh, Kirchhoff current law. So I naught will be this value will be or you can say this value Vs, or just use this loop equation. So this overall loop equation will be um, 4 plus J3 into I naught uh, uh, plus 2 minus J4, all this value into I naught plus Vs equals to 0, or sorry, minus Vs equals to 0. So eventually Vs it becomes equal to 4 plus J3 plus 2 minus J4 into um, I naught. So into I naught, and I naught is equal to 1 angle 0. So my Vs will be 6 minus J ohms. So this will be the Vs over here, and Is value is 1 angle 0 ampere. Oh, sorry, this is volts. This is amperes. So my value of Z Thevenin. So my value of Z Thevenin will be Vs divided by Is, and that is 6 minus J divided by 1 angle 0. This value will be equal to 6 minus J ohms. So this will be the value of Z Thevenin. So equivalent Thevenin circuit will look something like this. For this circuit, the equivalent Thevenin circuit will look, this is 6 minus J ohms, and the V-Thevenin value which we have calculated as 55 angle of minus 90 volts. So this is the, oh, sorry, if I have to redraw this line. So this is the equivalent, what they call the Thevenin equivalent. So whenever you have to ask you, that is the answer, the way you represent the answer. The equivalent, the Thevenin equivalent circuit for such a circuit will look something like this. Okay. So remember, in such a case that sometimes what you have to do is you have to calculate the maximum power transfer in such circuit. So for maximum power transfer, remember that your load, your the ZAB for max power transfer should be equal to ZAB be equal to Z Thevenin's conjugate. So what will happen? A conjugate for that will be equal to this. For maximum power transfer, your resistance, for example, this is with a minus j, so it means that it is a resistor and a capacitor. So for a maximum power transfer, your load must have a resistor and an inductor. So the resistors must match each other, and the capacitors and inductors must be the or must match each other in such a way that their impedances cancels out each other as in a net effect. In that manner, what will happen that you will have a purely resistive sort of circuit, and your there will be no back and flow force of power, and whatever your source is supplying, maximum power will be delivered at the load end. And so this is extensively used in this sort of analysis, and that concept goes beyond, or that concept is basically, and or sorry, this concept is extensively used in many different circuit analysis techniques, especially when it comes to antenna design or matching concepts in microwave circuits. This is extensively used and extensively deployed method of analysis and design. So moving ahead, uh, example 10.10. So in this circuit, we are asked to obtain a Norton equal or equivalent, or I not using Norton theorem. So remember, Norton theorem is the inverse of a Thevenin theorem. Again, it is used at two different terminals, and but in such a case, we have an I Norton instead of V-Thevenin, and a parallel, uh, like we can call it Z Norton or impedance Norton across these two terminals. And this would be something, or the equivalent model should look something like this for this. So this is how Norton theorem or Norton equivalent should look like. So for this circuit, to solve, first of all, we take the branch AB out. Take the branch at AB out. So my circuit will look something like this. So my circuit will look something like this. This will be V A B, or whatever the voltage over AB. So now we're not basically concerned with the AB here. So this is how this circuit will look if I'm going to take this branch out. This is 5 ohms. This is 8 ohms. This is minus 2J. This is 3 angle 0. This is 10. This is J4. So this is how the circuit would look. So now, first of all, we have to calculate two things. So we have to calculate Zn, and number two, we have to calculate I Norton. So these are the two things we have to calculate. So first of all, again, what is the impedance that is over here, or Z Norton is equal to what, or the technique is the same as we find out Thevenin. So for that case, again, remember uh, the current source, open circuit, and voltage source as a short circuit, right? So an open and short circuit, this whole thing will look something like this. So this current source, this thing is open circuited, this is over here, and this voltage source is short circuited. This is 10 and this is So we have to find out the Z Nortons between A and B. So this is 5, this is 8 minus J2, this is 10, this is J4. So this is what the circuit that remains. So if we have to find out the equivalent circuit, uh, this equivalent circuit is what? So if we are, or say for example, if current is flowing from here, the current will come here, tries to go there. There is an open circuit, no current flows in this branch. So I basically remove this branch. So comes here, goes through this 5 ohm, goes here. So can go over here and it can go over here. So this is a short circuit path. So there no current will be flowing over here. So the overall current path will be this. So my Z Norton will be equivalent to, or the current will see a resistance of 5 ohms only. So this is how it goes. So Z Norton, we have calculated Z Norton is equal to 5 ohms. So now we have calculated the Z Norton. Let's find out, uh, sorry, I Norton. So I Norton can be found out using multiple techniques. So we have these two circuits. So in such a case, when we have a current source in between two uh, meshes, so one, or it can be treated as a super mesh. One is this and the other one is something like this, or you can use this. But sometimes the super mesh technique becomes a little uh, difficult to handle and difficult to uh, uh, you can say use for different students, and usually they have issues in using these techniques. So the best way in such a case is to uh, use superposition concept, which we have seen in our previous lecture. So superposition, uh, so in that in this use superposition concept. So in that case, we first use see the response only because of the voltage source, then we see the response only because of the current source, and in the end we linearly add both of these current source. So first, using current source I equals to 3 angle 0 as source only. So using only as I as source, what we will be left with will be left with something like this, uh, and this voltage source is short circuited. We have this, this, and these are our two terminals, A and B. So remember, this is 5, this is 8, this is minus 2J, this is 10, this is 4. So I Norton is basically this current that is flowing here. So with I'm using only one of the sources, I call it I dash, I n dash. So what this value, what will be the value of I n dash? So remember, this section of the circuit is short circuited. So no current will flow in this section. All the current shall flow through this IN. So IN dash value will be equal to 3 angle of 0 ampere. So this will be my first value for IN. So now let's find out the value of IN because of this 40 angle 90 source. So B using uh, uh, yeah, sorry, finding you, oh sorry, B case is using V equals to 40 angle 90 volt source only. So this value again, if I'm going to use this, so what will happen? The current source, remember, you have to open the current sources and short the voltage sources. So this current source shall be opened, and this is the voltage source that is remaining over here. So this is the voltage that is B, and what I have to find out, I have to find out this IN, and let's call it IN double dash. That is because of this voltage source. So this is open circuit, so I'm removing this two. So this is how my circuit would look like. This is 5 ohm, this is 8 minus 2j, this is 10, this is j4, and this is 40 angle of 90 degree volts. Now this is how it is. So how this circuit would look like. So in double dash, this in double dash, or if I'm going to uh, draw the circuit, this circuit is something like this: 8 j 10 4. This is one part, and from this point to this point, so from this point to this point, this is only 5, and this is I and double dash. This is 5, this is 8, this is 10, this is minus j2, this is j4, this is 40 angle of 90 degrees. So technically 40 angle 90 degrees over here. This is the or we have to calculate the current through this uh, network. So I n double dash will be equal to voltage divide. This is the voltage, and this voltage is same across this 5 ohm. So voltage divided by the loop resistance. So that is 40 90 degrees divided by this loop or this branch is 5 ohms. So this will be 8 angle of 90 degrees, and I can also write it as J8 amperes. So I n double dash. So eventually I have found out both, we have found out both IN and IN dash and IN double dash. So my I Norton will be equal to uh, it was 3 plus J8 amperes. So this is the value of I Norton I have. So I will move ahead. So this is no, we are not solving example 10 here. So IN is, or I Norton, which we have found out as 3 plus J8. Similarly, Z Norton we have found out to be 5 ohms. So my equivalent, Norton equivalent, or then remember, we have to find out this I naught as this as our last step for the circuit. So my Norton equivalent for this circuit would be I Norton divided, and then comes Z Norton. And this is my A and B branch. This is my A, this is my B, this is my 3 plus J8, and this Z Norton is equal to 5. This is I naught. And for the branch AB, we have 20 ohms, and we have a 20 ohms, and we have a J15 ohms resistance. So what we have to do, we have to find out I naught. So remember, I naught will be equal to uh, use the current dividing rule using current divider rule, or you can also call CDR, current dividing law, or CDR, current divider rule, yeah, law, CDL. This will be 5 divided by this 5 divided by the complete impedance, 5 plus 20 plus J15, multiply by the current that is applied by the source 38. So just using this, my overall value will be 1.465 angle of 38.48 degrees amperes. So this is how you calculate the Norton A, or the I naught value for this circuit that is shown in this equation using the Norton theorem or Norton theorem based analysis for the circuit. So remember, again, this is how we solve the circuit. So here we have completed chapter number 10 of our textbook. We have seen examples for almost all the techniques that are used in circuit analysis uh, uh, to solve AC circuits for steady state analysis, and by using the phasor method. or by converting the circuits into phasors first, and then using different circuit analysis techniques to solve them for steady state analysis only. So remember again, when we are talking about phasors and we are converting our circuits into phasors, we are unable to extract the transient information out of them. We'll always be able to get to know the steady state values for the circuit. So here we'll stop. In our next lecture, we'll start from chapter number 11. Thank you very much.